The 344-gram model rocket shown generates 4.08 newtons of thrust. It spins in a horizontal circle at the end of a 42.3 centimeter long, 216-gram rigid rod. What is its angular acceleration? Let's state all of our variables. It's a little bit, okay, no thank you. It's a little bit tough. So we have our m, which is going to be our mass. It is equal to 0.344 kg. Make sure you guys do convert this. Remember, this is in grams. You want it to be in kg. We have the force that is generated by the thrust. That's 4.08 newtons. We have the length, which is equal to 0.423 meters. Make sure you guys also convert that. This is in centimeters. You have the mass of the rod, which is going to equal 0.216 kilograms. And then you have the angle, which we're just going to call angle, which is equal to 45 degrees. Cool? Cool. Okay. Remember the Z method, this right here. No, that's not what I wanted to do. It's not going to work. Okay. Just please stop. Okay. The angle that this line makes with over here, this angle over here, this angle theta is the same as this angle theta, just to be absolutely clear. Just something to be said about it, I guess. Anyways, well, the first thing that we're going to do is we need to calculate the torque generated by the thrust, okay? And we do this by doing the perpendicular force. So force, this is kind of like the perpendicular symbol. And that's going to equal our F times our sine 45 or theta or whatever you guys have. I think we all have the same angle. And then you should get some F perpendicular, okay? So this is the perpendicular component of the thrust force. Now we need to do the torque, right? Your torque, and watch this. Okay, you know what? I'm going to do this in color so that we can actually do this real quick. This is going to be F perpendicular. Your torque is equal to F perpendicular times your length, which should give you some kind of value in Newton meters. Okay, I'm actually going to give this torque some color because why not? Let's do a pink. I like pink. Okay, torque. Now, the next thing that we need to find is the moment of inertia. Remember, our moment of inertia is very important because it is how much an object will resist torque, okay? So the total moment of inertia for this system, it includes contribution from both, lost my notes for a second there, from both parts of the rocket, okay? So we need to find the moment of inertia of the rod, which will be, let's do green. I, rod, which is going to be equal to 1/3 mass of rod. Why am I doing this in this color? I have no idea. Plug that in. You should get an answer in kilogram times meters squared. Okay? Oh, I forgot. You also have to have, I messed up this equation, guys. Careful. You guys will get the wrong value. Okay. You also have to have an L squared in here. Okay. Let me hold on to all of those. Just gonna change their color so that we know that we're plugging in numbers that we already have. Can you please just change your color? You do that again. Okay. Change color. Thank you. Okay, anything in purple means that we already have the values for that. Then we want to find the inertia of the rocket. I rocket, which is going to equal the mass of the rocket, L squared. Remember, the reason that this one has a 1/3 at the top of it is because the center of mass shifts due to the rocket being attached to the end of it. Okay. Now we have ml squared. You should get an answer in kilogram times meter squared. As you guys will notice, I'm not actually solving it, so make sure that you guys plug in and find all of these values because you guys do need them. And then our last step is actually to calculate the angular acceleration, because now that we have the moment of inertia, we have the torque, we can use the equation and look at this handy dandy little trick. Torque is equal to the moment of inertia times the angular acceleration, which means that when we go to solve for the angular acceleration, we literally all we have to do is rearrange this equation and we get angular acceleration is equal to the torque divided by the inertia. And then you should get some kind of answer in radians per second squared, because remember we're doing revolutions. Revolutions are done in radians. And you should get your answer like that.